What an incredibly rare occurrence. A lunch hour office hour. You know, weirder things have happened in the world, but more normal things too. It's probably going to be short. I say this a lot. I've been saying this a lot
An
lately.
incredibly rare.
But you know, that's not always true. I don't always tell the truth. So you got to be careful about that. Yeah. So, what are some things I've been thinking about that I want to talk about or compute? I was talking with a friend and colleague this morning about computing some X groups. So maybe I could try and hack through that, or at least talk about where I got stuck with those computations. Because they're tricky. Because they are tricky. Maybe I'll open up some of those. Let's go. Let's take a look. No, that's not in here. That's in research notes. And yeah. Let's see. Let's have a little look-see over here. I guess the problem is I want to compute some modules. It is late, Nicholas. It is late. Not the latest office hour I've ever done. I've done office hours in the PM before. Not typical. Hello, Boris. Actually, why don't we look up? Let's see if we can collectively make sense of what is it? Projective resolution affine Hecke algebra. If I could do some of these computations, that would be ideal. That would be ideal. But it's tricky, you know. It's very tricky. Because why? Well, let me open up my notepad. The affine Hecke algebra is generated by you've got elements, one for each element of your vol group, which for GLN is Sn. And then we've also got these elements for, depending on what version you're looking at, we've got, co-characters. And, well, I guess for GLN, there's really, there's n of these that we want to, that we need to compute with, right? And, how do I say this? The kinds of Hecke algebras I want to compute are generally of the following form. So there's like a Hecke algebra of some like GLN. And then there's a Hecke algebra of a levy, which is really just a tensor product of a bunch of smaller GLNs. And then, tensoring up some module over there. So, for instance, in the case of GL2, I tensor up over the Hecke algebra of the torus, and those are just all these one-dimensional modules. And in the case of the Hecke algebra for GL2L, our Weyl group is just S2. So there's just the trivial element, and then this one, corresponding to the one non-trivial, one of these elements corresponding to the non-trivial element of the Weyl group. Hello. Non-trivial element of the Weyl group, and then there's two co-characters we need to compute with respect to, right? Where EI, or say E1 X will be X1, E2X will be 1X, for example. Right. But then, so if we take one of these like one-dimensional representations and we tensor over this, these two things span the subalgebra, so those are entirely determined. And so upstairs we just have there's two basis elements, one tensor 1 and TS tensor 1. And so, however, e to the epsilon I acts on 1, 1, because that belongs to the subalgebra, it'll just be one tensor, like whatever scalar you get from this action. And then it's very clear how TS, maybe not very clear, but TS, of course, will just send this to the other basis vector. That's easy. And then TS, by the way, is determined by the quadratic relation. So that implies that TS squared is Q minus 1 TS plus Q. So that tells you exactly how TS multiplies this other basis element in the module. Q minus 1 TS tensor 1 plus Q 1 tensor 1. And then finally, to totally determine the module, you just need to know, the multiplication's not commutative, but if you know the exact, there is a rule that tells you how to push this over to the other side. So the multiplication is completely determined. But let's take a look at this question in chat. Please help you on this. GCD of AB is equal to E. Can you write it that the GCD of A over E equal and B is 1? Okay, so you want to know if this is true. That should make sense, right? That should make sense. The biggest thing divides both of them, and then you're totally taking that out of A. That makes sense that this would be 1. So how could we prove this? Well, we could just try doing it directly using the definition, right? So, what's the best way to say this? The way I'm thinking is just suppose, right? So how could we prove this? If we could assume that we had a common divisor of A. Assume we had a common divisor of both of these. In fact, a common prime divisor. Yes, that's true. That is what the GCD is. Then we could argue that has to be 1, right? So, yes, exactly. Fundamental theorem of arithmetic for a quick unfun proof. Yeah, that's what I would probably do, right? So I would say something like, by the fundamental theorem of arithmetic. We can choose primes. Yeah, gosh, this does not seem like the best way to write this, but yeah, I can't think of a better way. No, maybe there is a better way. So, yeah. So okay. Maybe we could do something like this. So yeah, I would argue. Okay, let me finish this train of thought, anyways, at least to give you the initial idea or strategy. Basically, the first thing that comes to mind is use the fundamental theorem of arithmetic. You get some prime decomposition, like do the same thing for B and E, and then you also you factor E into these primes, right? F1, Q, S. Right, but then you basically argue that, well, actually, because E divides A, then you know that actually you can write E in the form where it's the same primes, and then, of course, F is at most, Fi is at most the value of EI, right? And then, yeah, basically the point is you need to assume, so A over E is then going to have a prime factorization of the following form. Right? And then you argue that, you suppose you have some P that's a common divisor of A over E and B. And yeah, let's see. E is the GCD. Oh, right. Yeah, maybe there's an even easier way to do this. Because if you assume that, right. So if you assume, suppose D divides A over E and D divides B. Well, then that implies that... No, maybe I'm talking crazy. No, I was talking crazy. Let me finish this train of thought. Yeah. So, sorry. Coming back to this main train of thought. Yeah, do I really need to write down a factorization of B as well? I guess we need to write down a factorization of B, right? So we could say that B, we might also want to write it in terms of, say, primes P1 up to PR. Where, of course, we're allowing these to possibly be 0. And then maybe we have some additional... Gosh, what's the best way to phrase this? I keep changing my mind halfway through about the best way to go about things. But anyways, the idea is so suppose, sorry, I got myself turned around. Where are we here? Right. So we have A over E. So we suppose we have a common divisor of A over E and of B. Okay, let's just write this out properly from the beginning. Okay. Suppose the GCD of A and B is equal to E by the fundamental theorem of arithmetic. We can factor A to P1 up to PR, B into Q1 F1 up to QR FR, and E into, gosh, too many letters. What's another good letter for a prime? L. LG1 up to, no, that shouldn't be R. There should be S. LTGT. You think from the inequality will be the minimum? Will that work? You think from the inequality Fi less than or equal to Ei, then I don't see how your second inequality follows. Why would Ei minus Fi be at least 1? So I don't think your second equality follows. And the GCD will not be equal to that. Although I think you have the right idea, right? You are right that the GCD, so the GCD will be, if we extend, okay, so we can do this. We can so you're right. If, like, let's say we choose factors, we choose a prime factorization. Like, we can make it the same number of primes if we just allow that some of these exponents are 0. And then you are correct that the GCD of A and B will then be the product from I equals 1 to R of PI to the minimum of EI and FI. So I think perhaps that's what you mean. Yeah, so that's certainly the case. And then we know, so the GCD of, GCD A over E B is going to be the product of P to the minimum of EI minus GI and FI. That's certainly going to be true. And then, we could conclude the proof. A12 and B equals 18. Wait, is this... Are you proposing a counterexample, Boris? A12, B18, GCD of 12 and 18 would be 6. A4 and B2. Well, I already started this one. So then GCD of 12 over 6 is 2 and 18. Counterexample. Yeah, so it's not even true. There we go. Hmm. Right. 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 Yeah, I guess yeah. It would have to be true. It could only be true. I mean, based on what we wrote out here, it would have to be true. It could only be true if for each I, the minimum of EI minus GI, FI were 0, right? And then, well, certainly, so that leaves us two cases. Either FI is 0. Right. Yeah, that makes more sense. Yeah, that makes more sense, Boris. Yeah. Yeah. Right. So if so possibility one is that EI equals GI, which would imply that FI. So FI we know has to be at least GI, which is equal to EI. So that's one so that's one possibility that these could be 0. Oh, you actually knew there were counterexamples? Well, come on. Why did you say that then? Why did you ask me to prove something that you knew there were counterexamples? But in the question, the author was trying to use this to prove something, to use some other thing. Well, are you sure? Because now I wonder. I mean, hey, maybe authors, maybe authors, authors make mistakes on occasion. But I also wonder, maybe you misunderstood what the author is saying. Also, who's the author? Are you reading a random PDF online, or is this from a book? Because books are always true, and online is always false. You're thinking of pursuing Hodge theory and work on Hodge conjecture. Nope, can't help you. Good luck. What's my advice? Be really smart and work really hard. Yeah, that's all I can tell you. I don't know much about Hodge theory. Yeah. 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 But let me complain to you about my Hecke algebra problems more. How about that? Because what's the case I'm trying to look at now? I guess, you know what? Maybe it's not as bad as I thought, but I guess I need to compute some X groups of modules, and that can be really difficult. That can be pretty difficult in the cases I'm looking for. Number theory by Kenneth Rosen. Proof on Grothendieck's sassy paper title. What's his? Oh, about the rational Hodge conjecture being false or something? Kenneth Rosen. There we go. Can you give a more precise reference though? Elementary number theory, is this the one? Can you please give a precise reference to the theorem or proof that you're in question? In the meantime, I'll go back. Homological algebra for affine Hecke. Maybe this is the one. Okay, but can you please give a precise reference for the proof, like page number or like lemma, blah, 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 point, blah, blah, blah. That would help me answer your question. Yeah, let's take a look here. I think this paper gives some ways to. Yes, X groups. This is what I want. Tempered modules. To prove one, we construct explicit resolutions. Oh, yes, right. Yeah, Hodge's general conjecture is false for trivial reasons. Right. Yeah, that's fantastic. That is fantastic. Yeah. Oh, right. I forgot the Euler-Poincaré pairing. I don't know if I tried exploiting that in my difficulties of establishing some X groups just yet. Dimensions of certain X groups. Yeah, I don't think that's going to get me anything more than what I've already done. Yeah. Chapter 3, prime, under exercise 3.5, question 122. Okay, let's go take a look. Or sorry, page 122. Where'd that book go? Page 122. 2. Bam, that's the wrong 122. Okay, 122. Exercise question number 6 edition, the book your web you showed. Yeah, question number 36. I see. Okay, so it looks like the question here, though, this is different than what you said in chat. This is a different thing than what you said in chat. Right? So what you said in chat was if GCD of AB is E, it implied GCD A over B equals 1. So that seems a little different than this question. Show that if AB are positive integers, then there are divisors, C of A and D of B, which are relatively prime. And that's their notation for LCM, I guess? And whose product is the LCM of A and B. Assume for contradiction that there is some factor D of A. Well, we already found a counterexample, Avery. So the original claim can't be true. Actually, what you asked the first question, the author uses. So can you explain what you mean by that? Because this is I don't. What do you mean the author uses this one to prove it? Actually, what you asked the first question, the author uses this one to prove it. Like, there's a solution to this somewhere? Where are you saying that the author uses that to prove it? Where is that? In the meantime, I'm going to keep looking at this Hecke algebra stuff. Problem is, I want to do some computations for GL4, and the problem is GL4 already gets fairly messy. But I could reduce some computations. Possibly to GL2 or GL3, but you know, life is easier there, theoretically. The affine Hecke algebra, unique complex associative algebra with this basis and relations, yeah. Yeah, I guess the problem is there's a bunch of adjunction tricks I've been trying to use to prove things. But the problem is I might just need to compute what on GL4? Well, basically I want to compute the X groups of some representations on GL4. I want to compute the X groups of some representations. Okay, number theory, Kenneth Rosen solution manual. Student solution manual on the Internet Archive. I'm not bothering going through these kinds of I hate these kinds of documents that aren't just a PDF. That's a nightmare. If that's what I have to look through, I'm sorry, then I can't help you. I just can't. Oh, is this the solution manual? Okay, maybe this is maybe this is doable if this is the solution manual. GL4 should be feasible, or are you too optimistic? I don't know. The problem is I mean, the Hecke algebra's got a lot of generators and relations, right? So let me just see if this is the right thing. What are we looking for? 7.7. Control F. Where are we going again? 5.3. Ah, no. No. I don't know. This is too much of a pain. I got stupid ads popping up. So I think, yeah. So let's go over here and yeah, I don't know. I think it's too much of a pain to dig up the solutions right now. I mean, maybe they're just making a mistake. I guess maybe they're just making a mistake. But let me talk a little bit about why GL4 is complicated. So I mean, well, first off, our the group is S4. So that means that we've got, I mean, well, actually, that's not true, but we only need the generators, right? So I guess we have the generators coming from the simple reflections. So I guess there's only 3 of these. So that's maybe not so bad. 1, 2, 2, 3, 3, 4. I guess that's not so bad. And then we have the 4 co-characters. So maybe that isn't so bad. And I guess I should add that the irreducible. Yeah, sorry I couldn't be more helpful. Um, and we have the irreducible representations I'm after. They can be written as being induced from. So we have the by taking a tensor product over the Hecke algebra of the Levy GL2 cross GL2 up to GL4. So so I guess to determine the dimension of these, we really have, I guess, yeah, maybe these irreducible representations should each be only two-dimensional, right? Because both of these are in the image of this inclusion. So maybe it's not actually so bad. Maybe it's actually not actually so bad. But I guess the one thing where the pain comes in, because I was thinking like one can do a really basic way of computing these. So for example, like if we go down to the Hecke algebra, so let's say we had a character of the torus, and we look at the corresponding affine Hecke algebra, right? So in this case, this is just H11. In this case, this algebra is actually just isomorphic to Cx plus or minus Cy plus or minus, right? And so if you have two characters, so every character is just completely determined by where, right, we have our two generators. And basically these two can get sent to any scalar you want. So this is like X corresponds to this and Y corresponds to this, right? And so basically a representation is going to be completely determined just by deciding where you send X and Y to, right? Basically just like by the evaluation map to some pair of complex numbers A and B. So then one can explicitly determine the possible extensions because you know that this thing, we know that well, basically, okay. So the simples are one-dimensional. So if we take some extension, it should be two complex dimensional, and it should have some subspace. So we know that we can pick a basis. Basically, if we think about X as like an operator on this extension. So maybe we have two characters. It's like chi determined by alpha beta, and we're trying to compute some extension, and there's like chi determined by gamma delta or something. So we know that we can choose a basis where in order to have it like as a subspace, X should be a matrix of this form where I guess it's alpha, beta, and then some mystery number up here. And wait, no, I guess it's X, alpha, alpha, and then Y will be acting by beta, question mark beta. Is that true? Something like this, right? Or maybe this is oh no, perhaps this should be determined by, sorry, I guess this should be gamma. And this should be delta. Right, so one can then do like a very explicit computation to basically, of course, there's the choice where if the question mark is 0 in both cases, that corresponds to the split extension, where it's just the direct sum of these two things. And then one can work out the possible distinct isomorphism clauses here. And I guess sort of this is very, very naive interpretation, but I don't know if I call these parameters like S and T. You can see that roughly this is like, this sort of depends on two things, and so you can predict that the X group in this case is going to be two-dimensional, which it is actually. It's provably true that this will be two-dimensional in this case. Looks believable enough, mostly for X stuff. You've seen as eye-watering manual computations only. Yeah. I don't mind doing these crazy long, insane manual computations, but it would just really be nice to have. I don't know. I want to have more examples. There's a whole bunch of work I've done that it's like, if I can just compute a couple X groups by hand, then I can leverage that to do some tricks to get a lot more X groups. Just bouncing off some tricks. Right, so here's. I mean, this is not fully rigorous. It's a bit of a naive computation. So this would be one possibility, right? But then, yeah, the thing is, when we go up here, I guess it's not so bad because each of the matrices of these things, is only 2 by 2. Well, they're going to be, see here it gets gross, right? Because so the irreducible module is going to be complex two-dimensional. So then what I need is a 4 by 4 matrix. But then, down here, for example, it's not so bad because I'm just computing like what happens with 2 by 2 matrices. But then up here, it's like I have 3 generators, 3 plus 4, so I have 7 generators, and each of those are 4 by 4 matrices. And then basically those computations like get cut down. There's some relations that, okay, we'll cut down some of the entries of the matrix, but it's just like, okay, a naive approach at this level just seems untractable, right? Like, yeah. So then, what next? I don't know. A naive approach at this level seems intractable, but I'm not sure what else to do. There is, mind you, there is some sort of a junction formula. So there's like Frobenius reciprocity, right? We have Frobenius reciprocity. I always forget what side these things go on. So where one is induction and the other is like restriction. J for the Jacquet functor, it's called. And so this corresponds, I mean, this is at the level of representations, but so in the level of Hecke algebras, it should just be restriction of scalars. So maybe it's also bad to compute the restriction of scalars. I'll have to think about it. What's going on? Just joined? Well, I was just about to take off, actually. I have to run to campus. I have a meeting right away. But tomorrow we'll continue. Maybe I will. Maybe I'll look at the restriction of scalars computations, and we'll be able to do it. Projective resolutions of representations of GLN is certainly known. Yeah, I don't think so. I mean, I should say that this is p-adic GLN. These are like smooth representations of p-adic GLN, and Yeah, I don't know. Like I've seen there's like one paper that explicitly determines dimensions of X groups in a very special case, and that's about all that's out there. So, anyways, go prove some.